All right, let me ask you something real quick. Have you ever walked into a building and just trusted it? Like, you don't stop at the door and think, is this thing going to collapse on me today? You just walk in, sit down, maybe even jump a little on the floor, and you assume, without thinking, that everything is fine. But here's the crazy part. That confidence is not accidental. Every building you walk into is quietly doing a job, a very serious job. It's fighting gravity, it's dealing with wind, sometimes even earthquakes. And it has to do all of that every day without failing. So today, we're kicking off something simple but powerful. What does a structure actually need to do? Not in textbook language, not in engineering jargon, just in plain English. So, what is a structure really? Forget complicated definitions. A structure is just something that holds things up and keeps them in place. That's it. A house, a bridge, a parking garage, even a shelf on your wall. If it carries weight and doesn't fall apart, it's a structure. Now, here's the real question. Why don't buildings collapse? Because honestly, if you think about it, they're not that thick. A floor slab might be, 20 centimeters? A column might look pretty slim. And yet somehow they're holding up people, furniture, equipment, sometimes entire floors stacked on top of each other. So what's going on? The hidden job, carrying and moving forces. Let me explain. Everything in a building creates force. You standing on the floor? Force. A sofa? Force. The building itself? Force. All of that force has to go somewhere, and the structure's job is to create a clear path for those forces to travel. Think of it like a delivery system. Floor sends load to beams. Beams send it to columns. Columns send it to the ground. Boom. Done. If that path is clean and continuous, everything works. If that path is broken, that's when things get ugly. One simple rule. You can remember this forever. Every force needs a way down. No path, big problem. That's when you see things like cracks, sagging floors, or in worst cases, collapse. So, what does a good structure actually need to do? Let's strip it down to the basics. At the end of the day, every structure has to satisfy a few simple requirements. Not 10, not 50, just a handful. 1. It must not collapse. This is the obvious one. If the structure fails suddenly, nothing else matters. Engineers call this safety, but let's keep it real. It just means no matter what happens, this thing should stay standing. And not just under normal use. It has to handle heavier loads than expected, strong winds, people doing dumb things, because they will. So we always build in a buffer, a margin, because real life is messy. 2. It has to feel solid. Here's something people don't think about. A building can be perfectly safe and still feel terrible. Ever walked on a floor that feels bouncy? Like slightly springy? Technically, it might be fine, but your brain goes, yeah, I don't like this. That's because structures also need to control movement. Not too much bending, not too much shaking. It should feel stable. 3. It has to last. Buildings aren't temporary. Well, most aren't. They're supposed to last 30 years, 50 years, sometimes 100 plus. So even if everything works today, we have to ask, will it still work decades from now? Materials age. Steel can rust. Concrete can crack. Water gets in places it shouldn't. So the structure has to survive time, not just loads. 4. It has to make sense in the real world. Now, this is where things get interesting, because in theory, we could make everything insanely strong, twice as thick, twice as heavy. Problem solved, right? Not really, because it would cost a fortune, it would be hard to build, and completely unnecessary. So engineers don't design for perfect, they design for smart balance. Strong enough, safe enough, but also practical. So, if we boil it down, every structure is trying to do this: stay standing, feel stable, last a long time, and not cost a ridiculous amount of money. That's it. That's the whole game. And here's the part most people miss. Structural design is not just math, it's decision-making, it's trade-offs. It's asking questions like, how much is enough? Where do we spend money? What's the real risk here? Because you can't maximize everything at once. If you push one thing too far, something else gives. What we're doing next. In the next parts, we're going to break this down piece by piece, not in a boring way. We're going to look at why buildings actually fail, why floors bounce, why cracks show up, and why engineers don't just make it stronger. Once you see it, you'll never look at a building the same way again. Next time you walk into a building, just pause for a second. Look around. That floor under your feet is carrying you right now, quietly, constantly, reliably. And if it's doing its job well, you won't even notice it. Which, honestly, is the whole point.
Now we're getting into the part that actually matters most. If you strip everything down, all the theory, all the calculations, all the drawings, there's one rule sitting at the center of structural design. Don't collapse. That's it. You can have cracks, you can have some movement, you can even have things that look a bit ugly, but the moment a structure collapses, nothing else matters anymore. So what does not collapsing really mean in real life? Because buildings don't just randomly fall down. There's always a reason behind it. And almost every time, it comes down to one simple idea. The structure couldn't handle what was happening to it. Let's talk about what a building is dealing with every single day. Every structure is under force, constantly. Its own weight is already huge. Then you add people walking around, furniture, equipment, maybe cars in a parking garage. On top of that, nature joins in. Wind pushes from the side, rain and temperature changes slowly wear things down. In some places, the ground itself can shake. And here's the part most people don't realize. These forces never stop. Not at night, not when the building is empty, not ever. Your building is working all the time, quietly, carrying everything. So how does a structure actually fail? It's not random. It usually follows a few very clear patterns. One of the most basic ways is simply too much weight. Imagine putting books on a weak box. At first, it holds. You add more, still fine. Then suddenly, it gives up and crushes. That's exactly what can happen to structural elements. When the force gets too high, the material just can't take it anymore. Concrete can crack and crumble, steel can permanently deform. At that point, the structure loses its ability to carry load.
Now we get into something people actually notice. Up to now, we've been talking about collapse, big failures, serious stuff. But here's the twist. A building can be completely safe and still feel wrong. Not dangerous, just uncomfortable, annoying, questionable. And that comes down to one thing: how a structure behaves while it's still standing. Let me ask you this. Have you ever walked across a floor and felt it move a little? Not collapsing, not cracking loudly, just a slight bounce. Like there's a tiny bit of spring under your feet. You pause for a second and think, is this normal? That feeling right there? That's what this part is about. Because structures are not supposed to just stand there. They move, every single one of them. When you step onto a floor, it bends, very slightly, usually so small you can't see it, but your body can feel it. Put more people in the same area, it bends more. Add heavy furniture, same thing. Even wind can make an entire building sway a little. And here's the key point. Movement is not a problem. Too much movement is. So the goal is not zero movement. That's impossible. The goal is keep movement small enough that people don't notice or don't feel uncomfortable. And this is where a lot of people get confused. They think if something moves, it must be unsafe. Not true. A structure can move a little and still be perfectly safe. But if it moves too much, people start to worry. And sometimes things stop working properly. Let's talk about the kinds of problems people actually experience. One of the most common is that bouncy floor feeling. You step down, and there's a slight delay. It dips, then comes back up. Structurally, it might be fine, but psychologically, it doesn't feel solid. It feels cheap or weak, even if it isn't. Another one you've probably seen is cracking. You walk into a relatively new building, and there it is, a crack on the wall, maybe near a corner, maybe above a door. Immediately, people think something is seriously wrong. But a lot of the time, those cracks are not about collapse at all. They're about movement. Different parts of the structure move in slightly different ways. Materials expand and shrink. Over time, small stresses build up. And the easiest way to release that stress? A crack. Then there are doors and windows acting weird. They don't close properly anymore. They get stuck. You have to push harder than usual. That's not random. That's the structure shifting just enough to change the shape of the opening. Again, not a collapse issue, but definitely a usability issue. So what's really going on here? It comes down to controlling deformation. That's just a technical way of saying how much something bends, moves, or changes shape. Think of a floor like a very shallow curve. When there's no load, it's flat. When you stand on it, it bends slightly. If that bend is tiny, nobody notices. If it's bigger, you start to feel it. If it's too big, it becomes a problem. Engineers set limits for this, not based on whether something will collapse, but based on what people can feel and tolerate. Because at the end of the day, buildings are for people, not just for calculations. And there's also a time factor. Some movement happens instantly when loads are applied, but some happen slowly, very slowly. Concrete, for example, keeps deforming over time under constant load. So a floor that felt fine on day one might feel different a year later. That's something designers have to think about from the start. Now here's an important mindset shift. Safety is about survival. This is about comfort and function, two completely different things. You can pass all the safety checks and still fail here.
And honestly, this is where people judge buildings the most. Nobody walks into a building and says, "Wow, the safety factor here is impressive." But they do say, "This floor feels weird. Why is there a crack here? Why won't this door close?" That's real-world feedback. So a good structure doesn't just stay standing. It feels right. It behaves in a way that people trust, even if they don't understand why. If you had to sum this up in one idea, it would be this: a structure should not only be safe, it should feel stable. And here's where it gets interesting again. Even if a structure is safe and feels perfectly fine today, there's still another question. Will it stay that way? Because time changes everything. Materials age, conditions change, small issues grow. So in the next part, we're going to talk about something people don't think about until it's too late. Why buildings get old, why problems show up years later, and why it works now is not enough. That's where durability comes in.
Now we're stepping into something people almost never think about until it's too late: time. Up to this point, we've talked about two things. First, a structure shouldn't collapse. Second, it should feel stable and comfortable when you use it. But here's the problem. Just because something works today doesn't mean it will work 5 years from now, or 20, or 50. Let me ask you something simple. Have you ever seen a building that looked tired? Not broken, not collapsed, just old. Maybe the surface looks worn, maybe there are stains, maybe small cracks everywhere. You look at it and think, yeah, this place has seen some years. That's not an accident. That's time doing its job. Because structures don't stay the same. They change, slowly, quietly, constantly. And this is where durability comes in. Durability is just a fancy word for one idea. Can this structure keep doing its job for a long time? Not just today, not just when it's brand new, but years and decades into the future. Here's the reality. The day a building is finished, that's the best condition it will ever be in. After that, it's all downhill. Maybe slowly, maybe very slowly, but things start changing from day one. Let's talk about what actually happens over time. One of the biggest enemies is water. Water gets into places you don't see, through tiny cracks, through joints, through surfaces that look perfectly fine. Once it's inside, it starts causing trouble. If there's steel inside the structure, like reinforcement in concrete, water can lead to corrosion. And when steel corrodes, it expands. That expansion creates internal pressure. Pressure inside the concrete, and eventually, cracks start to appear. Not because the building is overloaded, but because something inside is pushing outward. Temperature is another silent player. Materials expand when it's hot and shrink when it's cold. This happens every single day, day to night, summer to winter. Tiny movements over and over again. And over time, those movements add up. They create stress, they weaken connections, they open up small gaps that weren't there before. Then there's long-term deformation. Some materials don't just deform once and stop. They keep deforming under constant load, very slowly. So a beam or a slab might look perfectly fine at the beginning, but over months and years, it bends a little more, until one day, people start noticing. Now here's the important part. None of this happens suddenly. That's what makes it tricky. It's slow. So slow that most people don't notice until it's obvious. This is why durability is not about reacting. It's about planning ahead from the very beginning. Engineers don't just ask, will this work today? They ask, Will this still work decades later after being exposed to weather, use, and aging? That changes how things are designed. You might choose thicker concrete cover to protect steel. You might use better materials in areas exposed to moisture. You might design details that keep water out in the first place. Because once problems start inside, they're hard to fix. Here's a simple way to think about it. Strength is about surviving force. Durability is about surviving time. Two completely different challenges. And here's something a lot of people don't realize. Most structural problems in the real world are not caused by extreme loads. They're caused by time, by small effects repeating over and over again, by environments that slowly wear things down. Now, let's connect this back to real life. You've probably seen things like concrete with pieces breaking off, rust stains leaking out, cracks that seem to grow over the years. Those are not random. Those are signs that durability wasn't fully achieved. And once durability is compromised, something else happens. Maintenance starts, repairs, patching, reinforcement, and all of that costs money, sometimes a lot of money. Which brings us to an important idea. A structure is not just built once, it's something you live with for years. So a good design doesn't just reduce risk, it reduces future headaches. If you had to sum this up in one clean sentence, it would be this. A durable structure is one that keeps doing its job year after year without falling apart from the inside. And now we've got an interesting situation. We've covered safety, we've covered how it feels in use, we've covered how it survives over time. At this point, you might be thinking, why not just make everything stronger, thicker, and more durable? Problem solved, right? Not quite. Because in the real world, there's another constraint that controls everything. Money. And not just money, reality. In the next part, we're going to talk about why engineers don't design perfect structures, why stronger is not always better, and why every design is actually a compromise. That's where things get very real.
All right, now we're getting into the part nobody talks about, but it controls everything. Reality. Up to now, everything sounds kind of ideal. Make it safe, make it feel solid, make it last a long time. Sounds simple, right? So why not just make everything stronger? Thicker slabs, bigger columns, more steel. Problem solved. Yeah, not even close. Because in the real world, every decision runs into limits. And the biggest one is money. Let's be honest for a second. No one is building with unlimited budget. Not homeowners, not developers, not governments. Everyone has a number. And once you go over that number, the project doesn't happen. So now you've got a situation. You want it to be safe, you want it to last, you want it to feel good, but you also need it to be affordable. That's where things get tricky. Because here's the truth. You can always make something stronger. Always. Add more material, increase the size, use higher grade stuff. There's no upper limit to stronger. But there is a limit to what people can pay. So structural design becomes a balancing act. Not about making the best possible structure, but making the smartest possible structure. Think about it like this. If you doubled the thickness of every slab in a building, will it be stronger? Of course. Will it be safer? Yes. Will it cost a lot more? Also yes. And not just a little more, a lot more. More material, more weight, bigger foundations, more transport, more labor. Everything goes up. So instead of asking, what's the strongest we can make this, engineers ask a different question. What is enough? That word matters. Enough. Strong enough to be safe, stiff enough to feel solid, durable enough to last, but not excessive.
because over-design is a real problem. It wastes money, and in large projects, that waste becomes massive. Now, here's another layer most people don't see. Even if you design something perfectly on paper, someone still has to build it. And construction is not a lab. It's messy. There are real people on site, real conditions, weather, time pressure, human error. So, if your design is too complicated, too tight, too precise, it becomes hard to build correctly. Let's say you design a beam with steel packed extremely tightly. On paper, it looks great, but on site, concrete can't flow properly between the bars. Air gets trapped, voids form inside, and suddenly your perfect design becomes a problem. So constructability becomes part of the equation. Not just can this work, but can this be built reliably? Good design respects the people building it. It gives them enough space, clear details, reasonable tolerances. Because a design that only works in theory doesn't work. Now, let's zoom out for a second. At this point, you've got multiple forces pulling in different directions. Safety wants more strength, comfort wants more stiffness, durability wants better protection, cost wants less of everything, construction wants simplicity. And they don't all agree. Push one too far, and another suffers. This is the part that makes structural design interesting. It's not just calculations, it's decision-making, trade-offs, judgment. You're constantly asking, where do we spend money? Where can we save? What matters most in this specific project? A hospital might prioritize reliability and performance. A warehouse might prioritize cost and speed. A luxury building might care more about comfort and feel. Same principles, different priorities. And that's why there is no single perfect design, only designs that make sense for their situation. Here's a simple way to see it. Imagine a slider with different factors: safety, comfort, durability, cost, constructability. You can move each one up or down, but you can't max them all at the same time. So the goal becomes balance, not perfection. And if you had to sum up this whole part up in one idea, it would be this. A good structure is not the strongest possible one. It's the one that achieves everything it needs to without wasting resources. Now, here's where everything comes together. We've talked about not collapsing, feeling stable, lasting over time, working within real-world limits. At this point, you're basically seeing the full picture, but there's still one final step: putting it all together into a single way of thinking, a simple lens you can use to look at any building and understand what's going on. That's what we're doing next. And once you see it, you won't be able to unsee it.
Let's bring everything together. Up to this point, we've been breaking things apart. We talked about why structures don't collapse. We talked about why some floors feel solid and others feel weird. We talked about how buildings slowly change over time, and we talked about the reality of money and construction. Now, it's time to zoom out and see the whole picture. Because here's the truth. Structural design is not just about calculations. It's not just about formulas. It's not even just about strength. It's about making decisions under constraints. Every single structure you see around you is the result of a series of choices. Not perfect choices, not unlimited choices, but practical ones. Let's simplify everything into one clean mental model. Every structure is trying to do 4 things at the same time. It has to stay standing, It has to feel stable, it has to last over time, and it has to make sense in the real world. That's it. That's the whole game. Now here's where it gets interesting. Those four things don't naturally line up. They pull in different directions. If you push really hard on strength, you usually increase cost. If you push really hard on stiffness, you might make the structure heavier. If you push durability to the extreme, you might overbuild and waste resources. If you try to cut costs too much, something else will suffer. So design becomes a balancing act, not solving a single problem, but managing multiple pressures at once. And this is why two buildings that look similar can be completely different behind the scenes. Different priorities, different budgets, different environments, different decisions. Now, here's a way to think about it that's super useful. Instead of seeing a building as a fixed object, start seeing it as a system that is constantly carrying loads, adjusting to movement, responding to the environment, and aging over time. It's not static, it's active, even if you can't see it. That floor under your feet right now, it's slightly bending. The walls around you, they're expanding and shrinking with temperature. The structure as a whole is slowly changing as years go by. And the only reason you don't notice any of this is because it's all happening within controlled limits. That's the real goal of structural design: control. Not eliminating forces, not eliminating movement, not eliminating change, but controlling it all so it stays within acceptable boundaries. Once you see it this way, everything starts to click. When you see a crack, you don't immediately panic. You ask, is this from movement? Is it expected? Is it within limits? When you feel a floor move, you don't assume danger. You think, is this just a comfort issue? When you look at an old building, you don't just see age. You see time, environment, and materials interacting. That's a completely different way of looking at the built world. And here's the part that most people never realize. Structural design is not about making things perfect. It's about making things reliable. Reliable means it works today, it works tomorrow, and it keeps working without surprising you. No drama, no sudden failures, no constant problems, just quiet performance in the background. And honestly, the best structures are the ones you never think about. You walk in, you use the space, you leave, and nothing ever feels wrong. That's not luck. That's design done right. So, if you had to take everything from this entire series and compress it into one idea, it would be this. A structure is not just something that holds weight. It's something that quietly manages forces, movement, time, and real-world limits all at once. Next time you walk into a building, try this. Pause for a second. Look around. The columns, the beams, the floor, the walls. None of them are there by accident. Every piece is part of a system. Every piece has a role. And if everything feels normal, if nothing moves too much, nothing cracks in a worrying way, nothing feels off, that means the structure is doing exactly what it's supposed to do. You just don't notice it, which, in this field, is the highest compliment you can give.